So, I made a video last week about how to simulate heterojunctions in the model, and the person who sent me that email asking me how to do that said, well, what I'd really like to do is simulate a slightly different device, which isn't just a plain heterojunction, but it's something a little bit more special. It's a heterojunction with an insulating layer on one side, and it's effectively some type of sensor. And he said, can you model this with the model? And I said, well, yes, and let me show you how to do this. And I think I quite like this format of answering emails with videos, because I can sort of talk about things and also demonstrate them at the same time. And also lots of people get to see these videos, which is better than just one person if I answer via email. So I might continue doing this. So I think I'll try and answer these sort of the pertinent questions as I get via email that like this in video format. So let's go and find this paper about this heterojunction. So let's move this out of the way. And here's a paper that the chap talks about, and it's called Optoelectronic Conversion by Polarization Current Triggered by Space Charges to Organic-Based Interfaces. Now, what this is, so if we look at the paper, so we'll just zoom out a bit and look down this paper, it's a nice little short letter, and if we look at this device structure that's in this paper, it's effectively an insulator. So this is, I don't know, some polymer thing. And you've got, so this is literally a polymer, this is not a conducting layer. You've got a insulator, so you're some type of, sorry, not an insulator, you've got your active layer here, so this is some type of organic semiconductor. You've got hole injection, sorry, electron injection here and hole injection here. And then the transients look a bit like this. So the question is, can we model this in the model? And the key thing about this is it's an insulator with some type of charge profile and an organic material. So let's try and have a go at modelling that in the model. So, let's look at the layer editor. So I'll try and make the layers look like the structure. In fact, let's put this up here so we can see what we're aiming at, basically. So we're trying to model this. There's me. Now, let's look at the layer editor. So firstly, let's this layer, this is actually the P dot layer in the default simulation. So let's rename this and call this insulator. And let's set this, the width of the insulator and the width of the active layer to be the same width. Now this isn't actually P dot, so let's change, so in this paper this isn't P dot, it's actually some type of plastic. So let's change this to PMMA, which is just some type of insulator. The contact in the default simulation is actually aluminium, and I've already actually set this to PMMA. So you must remember to do this, because obviously no light will be able to get through the metal contact. And let's make this a bit thinner too. Let's make the metal so we're looking at this layer here. Let's make this layer just a bit thinner. So let's make it 10 nanometers to make sure light actually gets into the device. I haven't read what material they use. I suspect it's glass or ITO or something like that, but you can play with that yourself. Let's make the insulator layer also active, because we want to solve the drift diffusion equations in there. And now if we zoom in into the device, we can see effectively we've got insulator and a contact. Yeah. So, right, now let's look at the electrical parameters. Now, we've got two layers, and what I'm going to do is basically set them to be as identical as possible. So let's start off with insulator. So we're going to say, okay, there's not many traps in the insulator because it's not conducting really. Mobility, let's set this to be low. So I'm going to set this to -10. Which is a very low mobility. Traps, let's make sure there's the same number of traps in both materials. You must have this, otherwise it won't work. Let's set this recombination cross section just to something sensible and symmetric. Same with the material, let's make it the same. Let's bring the mobility of the PC of the active layer up. Yep. And I don't like this being called PCBM. Let's rename it and just call it active. So what have we got now? Yeah, so let's look at the electron affinity. Now I'm just going to make these numbers. It doesn't actually matter what the electron affinity is. So this chi, it's the level of the HOMO effectively. Sorry, the LUMO effectively. It doesn't really matter what it is because it's all relative. Because if you if you have it, as long as you shift all materials by the same number, it doesn't matter where they lie in space. So I'm going to set this as 3 just for convenience. I'm going to set the band gap to 1. Now you might ask, why has the insulator got a band gap? Well, I'm going to come back to that in a minute. I'm going to do the same for the active layer, and we'll set this as 1. I'm going to set the effective density stays the same in both materials. So effectively now, let's just set this a bit lower. So there's a number of traps in the active layer, and let's just make the tail slopes for the traps the same energy. So we've now got effectively not 2 nice symmetric materials. Now, let's think about the device. So here we've got a device. Now, I've set this mobility in this material very low. So this is 1 to the minus 10, and this one high. So we've got 5 orders of magnitude difference between the mobility in these materials. But that might not be enough to stop charge carriers getting over into here. So what you really want is some type of a step in band gap, both in the LUMO and the HOMO, to stop charge carriers going between there and there. Now, realistically, if you think about an insulator, it's going to have a very, you're not going to be able to get charges into it at all, really. So you can sort of imagine it as having a very big step in in band gap at the interface, effectively, because you're sort of having carriers come in, and there's not going to be able to they're not going to penetrate it effectively. Now, it's the same with things like oxides and things like that. You might want to model a material with a very, very big step in band gap, like 10 eV or something. Now, that's very difficult to do numerically. Like, actually, the hardware of the computer finds it very difficult to model materials with a big band gap. And the reason for this is because you have, at an interface with a big band gap, like say 10 eV or something like that, you have a very small number of charge carriers sitting on one side of the interface, or a very big number. Now, what this means is in your simulation you've got a very broad range of carriers. So you might have here, for example, 1 to the 25 carriers, and here you might have 1 to the minus 25. Now, why this causes problems in a simulation can be explained as follows. So let's look at this example. So fire up Octave or MATLAB. Now I'm just going to do a very, very simple sum, and just the answer will be surprising. So I'm going to go 1 to 25, so 1 to 25 carriers, plus a very small number of charged carriers, and subtract a very big number of charged carriers. So this is just a very simple sum to demonstrate my point. I'm going to divide by 1 to the minus 20. Is that right? Yeah, no, exactly, right. So this is a little demonstration. So if you evaluate this as a human, so using your brain, evaluate this sum. So you've got 1 to 25, then subtract minus 1 to 25, so that's that and that together is 0, right? Then we go 1 to the minus 25 divided by 1 to the minus 25. So 1 to the minus 25 divided by 1 to the minus 25 is 1. So the answer to this should be 1. But weirdly, the computer gives us 0. So why is this? Well, the reason for this is because what's happened in this mathematical sum is that we've added 1 to 25 to minus 1 to 25. And because the computer doesn't have enough floating points to represent a number with 50 decimal places, it's said, okay, well, I've got a really big number, I've got a really small number, so therefore I can't be bothered to store this small number, just store the big number. Then this here is equal to 1 to the 25, then we've got 1 to the 25 minus 1 to 25 is 0, divided by this number is 0. So in this example, because of the floating point error of the computer's got the answer 100% wrong. So the answer should be 0 and we've got 1. The answer should be 1 and we've got 0. Now when you start thinking about sort of simulations like this, and you start having very big numbers of charge carriers here and very small numbers at the interface here, you start to have issues like that. You run into hardware issues basically with the computer. So the trick to get around this is say, right, well, we don't need a band gap of 10 eV. We don't need a jump in band gap to stop charge carriers going over in there of 10 eV. We can do with like 1 eV, because realistically the kinetic energy charge carriers have at room temperatures like 25 MeV. They're not going to be able to get over a barrier bigger than about a volt. So let's just, for simplicity here, introduce a step of, say, 0.5 electron volts to simulate that sort of that interface. So I'm going to move the electron affinity of the insulator up by 0.5 EV, and I'm going to increase the band gap, so we've got a step on both sides of about 0.5 EV. So I'm going to set this to 2.0. So I'm just going to draw what I have done. So we had something that was insulator, insulator I, the active layer was like this, and what we wanted was something like that. This type of step of say 10 EV is unrealistic, so what we've done is we've made a step of, say, I don't know, half an EV there. So that's what I've done. Right, so that's that sorted. Let's just look at the contacts. Now, in the default simulation, they're somewhat asymmetric, so this is just because it's a fit to experimental data, so I'm going to make them symmetric, just for ease of, yeah, I guess just ease of understanding the results. Now the final thing is we've got the light coming in from the top here. You can see the lights coming in from the top, so we want to make the light coming from the bottom. So let's go to configure and then set this to bottom, okay, and let's run a simulation and see what we get. Let's look at the JV curve. Well, that is a pretty horrible JV curve. I'm surprised it's that good actually. Let's double check why it's actually performing so well. Let's look at this. Yep. Okay, that's reasonable. Yeah. Anyway, so we've got a JV curve. I mean, it's pretty horrible as JV curves go. So yeah, now let's try and have a go at making these transients here. So what I'm going to do is go to the time domain editor. I'm going to edit one of these preset time domain. Oops, there's me. One of these preset time domain simulations. So let's go to TPC 50 millivolts 1 sun. Now, I don't know what conditions this sensor is running in, so let's go for dark. So we'll firstly set the light intensity to 0, so that's dark. Now what we've got here is a laser pulse. Now I don't think a laser pulse is appropriate for this. It looks here, it looks a bit slower. It looks, we're in milliseconds here, so it looks like something like a chopper. So what I'm going to do is turn this nanosecond, it's actually femtosecond laser off, so sensitive -1. The simulation, let's start the simulation. Here it starts at sort of negative times, and the reason for that because I was fitting to experimental data. So let's set this to 0. Now, it looks to me, put me out of the way there, it looks to me here like we've got the light source is off, it's on, it's off, it's on, it's off. So let's set up 4 regions here. So we've got 4 regions. Now, let's put 5 regions in actually, and I'm not going to do this time scale exactly. I'm just going to do microseconds because I think that'd be easier to do. But you can mess around yourself. So let's turn the voltage off to, let's make the voltage 0 because we don't want to be simulating a voltage ramp. That's C-live. That's something different. So now we're simulating at 0 volts. We've got the time step here is growing by 1.8 every time step, so let's set that to 0. So now we've got a consistent time step. I think that's this one. Okay, anyway. Now let's firstly model this region here. The first region here as, I don't know, let's say 100 microseconds. Firstly, let's set the time step to be smaller. Okay, let's model as 100 microseconds. And then let's turn the laser on for 10 microseconds. And then let's model another 100 microseconds. And let's turn the laser on for 10 microseconds. And then let's model another 100 microseconds. The graph's moving around here, but it doesn't matter really. And let's do steps of 0.5 microseconds just to speed up the simulation a bit. And so initially let's turn the light off, then it's on, and then here let's turn it on. Okay, I'm not actually sure what's going. Oh, it's a long light pulse actually. This is I see. So it's turn it on and then it's off. Okay, well, you can play with this to your heart's content. So that's that setup. So I've slightly misread the graph here. We've got 2 light pulses rather than just one, but you can go and play with this. Doesn't matter. So we've set that up. So this is called TPC 50 millivolts 1 sun. Let's flip the simulation mode to that, and then we could actually rename this. We could rename this to something else by clicking rename, but I think you might have to reload the file for that to take effect, so we won't do that. And then let's run it. Whoops, and that's doing the main simulation. And you can actually see, interestingly, if I move me again, you can actually see this is the time domain simulation, and then here is when it does sort of the full optical simulation in the middle, when it's sort of applying the light pulse. So let's look at the output. Oh, that's a bit weird. Let's look at that one. So time J is time current. Now it looks a bit weird. It looks negative because negative current is current that's coming out of the device, positive current is going into the device. So let's just go and plot this in GNU plot. I mean, you can plot this in your favourite Excel or whatever your favourite plotting program you want, but let's just go and plot this in GNU plot. So let's go time j dot dat using 1, 2. Let's invert the axis with lines and points. There we go. That looks quite nice. Now, one thing I think I forgot to do actually is set up the mesh correctly. So I think we should go back and look at the mesh. So here's electrical mesh. Now I've actually done this whole simulation with just 5 mesh points, which is probably not correct. So let's make 3 layers. Now we've got a layer that's, the active layer is 100 nanometers. So let's make one layer that's 95 nanometers. I'm doing this in octave just to make sure I don't mess up the number of zeros when I'm doing this in the video. So we're going to have 2 layers of 95 nanometers. Then in the middle, we're going to have a layer of 10 nanometers, and we're going to put 10 points in this layer. We're going to put 5 in this layer, and we're going to put 10 in this layer. And what this will effectively do is this just means we're going to be meshing very, very accurately over our heterojunction, so that the steep step is taken into account properly. So should we just rerun that? So now, just before we run that simulation, what I'm going to make sure is that the electrostatic solver is turned off. Now, let me explain this. So there's 2 solvers as part of the model. So there's an electrostatic solver and a drift diffusion solver. The drift diffusion solver, so this drift diffusion solver, inside it has an electrostatic solver. And so that therefore you can solve the continuity equations and the potential within the device correctly. So you'll be able to figure out where the charge is and where, how it's moving about. Now, before it runs that full drift diffusion solver with the electrostatics, it does one quick run with just a pure electrostatic solver. Now, sometimes it's very, very good and it makes the model more efficient, but sometimes this trying to solve this with just the electrostatic solver causes problems, especially with heterojunctions. So I'm just going to make sure before I run the simulation again that we've turned this off. So I've got enable Poisson solve, so I've just turned this off, and all this means is it's not going to try and guess the electrostatic field before it runs the main solver. It'll all be self-consistently solved, but it means we won't be running the Poisson solver alone before we run the simulation. So now I'm just going to run this. And I'm going to plot the result, and it looks a little bit different because we've meshed it properly this time. So that's it really. That's how to measure insulating devices with heterojunctions and do time domain simulation. So I hope that's helpful, and I think I will leave it there. Thank you very much.